Welcome back. Now today we will be going to go through the topic at kinematic indeterminacy. I am Dr. Atrayee Bandyopadhyay. Welcome to the lecture on kinematic indeterminacy today. From continuation for the last lecture of static indeterminacy to kinematic indeterminacy. So first we will know what is kinematic indeterminacy. It is nothing but the number of independent displacement components. We saw that the static indeterminacy is dependent on the unknown forces, whereas the kinematic indeterminacy is directly related to the number of unknown displacement, that is the degree of freedom. Okay, so the number of independent displacement components, that is the degree of freedoms in a structure after considering support constant. Okay, here also similarly the number of unknown displacement minus the number of available support reactions which generates as a result of restrained joint displacement. That means when a joint is restrained, like a fixed head, it is restrained in both this direction and this direction and this direction. So here there will be three support reactions. Okay. Similarly, these two are used to calculate the degree of kinematic indeterminacy. It is very important for the matrix method of analysis because kinematic, after getting the value of kinematic indeterminacy, when we need to solve the unknowns, how will we solve it? Because static equilibrium equation will not be enough to solve this. So for that, we will go to the matrix of method analysis, matrix method of analysis. That will help to solve this kinematic indeterminacy problem. With structures with kinematic indeterminacy can be solved using matrix method, which is a very complex problem. We will learn later on some other day. This is the basic equation for static and kinematic indeterminacy for different type of structures. For beams, that is 2D, Re minus 3, that is reaction minus 3 for 3 equilibrium equations in 2D. Frames, similarly 3 equilibrium equation for 3D, that is 6 equilibrium equation. Truss for 2D, that is 3 equilibrium equation for 6 equilibrium equation. Similarly, C is nothing but the number of closed loops. If this is a frame, then here this one is a closed loop. That means this will be the closed loop. That means for this structure C will be 1. Okay. Number of members, that is 1, 2, 3, 4, 5, 6, like this, 6 members. Number of joints 1, 2, 3, 4, 5, 6. Number of axially rigid members. This 1, 2, 3, 4, 5, 6, or in a beam we can simply say, if there is an internal hinge, this is one axially rigid members. Number of members connected are internal hinge. If there is a hinge internally, how many members are connected? Here, here. Okay, so like this, the whole equation system has been summarized in this table, which will be helpful for you to follow for complicated structures. Okay. From here we can deduct the value and we can calculate the external internal static indeterminacy as well as the kinematic indeterminacy. Now let us go for some examples. Simple example for static indeterminacy, like fixed beam. More reactions, less than equation. That is fixed beam. That fixed beam is nothing but this is a fixed beam. Fixed beam has a vertical reaction in both sides, horizontal reaction in both sides, as well as moment. That means 6 unknowns but equilibrium equation 3. That means 6 is greater than 3. That means static indeterminacy is 3. Static indeterminacy is 3. Similarly, another example is continuous beam over multiple supports, frames with redundant members. For trusses, when DS static indeterminacy is greater than 0, the truss is statically indeterminate. When ds is equals to 0, statically determinate exactly how much unknowns are there, how much the exact amount of equilibrium equation is there, and exact amount unknown is the same. That means the structure is exactly solvable with the equation. There is no extra equilibrium equation that is unused, that is unrequired of, neither there is extra unknowns that cannot be solved using the equation. That means the number of unknowns and the number of equations equally justify each other, and the structure thus becomes statically determinate. Okay. But when again ds is less than 0, that is static. The stress is unstable. So for 2D, from the last slide, we can see for 2D, the external, the internal, and the kinematic indeterminacy. Now here for 2D truss, we know static indeterminacy is m minus 2j minus 3. For truss 2D, here m minus 2j minus r. Here r is nothing but the reaction forces of our equilibrium equation. So what is the equilibrium equation here for r? For truss in 2D, r is nothing but 3, because in 2D the r is what? 3. How? In 2D r is number of that is 3. Fx0, Fy0 and moment 0. So r is 3 for 2D truss, and here therefore m minus 2j minus r becomes m minus 2j minus 3. For this truss, how many m is there? M means member. 1, 2, 3, 4, 5 and 6. Therefore m is 6. Now joint is 4 joint, and r is 3 equilibrium equation. That is 3 equilibrium equation, we all know. Therefore the degree of static indeterminacy becomes 1. That is the beam is statically indeterminate. Greater than 1, statically indeterminate. Now for this triangle truss, member is 3, joint is 3, and unknown equilibrium equation is 3, because we are going for 2D only right now. So degree of static indeterminacy means 0. That is exactly the number of unknowns and the number of solutions justify each other, and the structure becomes statically determinate. Similarly, for this square truss, joints are 4, 1, 2, 3, 4 members, and equilibrium equation is 3. So this is minus m. Then the structure becomes unstable. Okay. So similarly, when we calculate the kinematic indeterminacy, there is a very good example is the pin jointed trusses, because that truss will have degree of freedom at the joints, and beams and frames with rotational and translation degree of freedoms are also included in this type of calculation for kinematic indeterminacy. Like example, for a beam, the formula is kinematic indeterminacy 3j minus r minus mr plus rr, where re is the equations, j is the joints 1, 2, 3, and here is an internal hinge, that is the fourth joint. Therefore 1, 2, 3, 4, j is 4. Okay. Now we can see that here 3j minus re minus m dash plus r. Now what is the rr? That is the number of releases. Re is number of reactions external, and r is number of releases. That means internal hinges, reduction in stiffness. This includes this section. So rr is nothing but the summation of m double dash minus 1 for 2D and 3m double dash minus 1 for 3D. What is m double dash? M double dash is number of members connected at internal hinge location. Okay, now let us go for the problem. Now internal hinge location is here. Here there is one side and here there is another side. That means two sections of it, beam has been joined here. So therefore m double dash is 2, 1 and 2. And here therefore RR is m double dash minus 1 formula wise, and this is 1. Okay. Now RE is 4. How RE is 4? Here that is a pin joint. There will be one reaction, two reaction. Here there is a roller joint, only one reaction. Here is also a roller joint, so only one reaction. So therefore the number of reactions became 1, 2, 3 and 4. Okay. Similarly, we have got RE, J, M double dash, and for using M double dash we got RR and M dash. So here using this formula we can directly calculate the kinematic indeterminacy of the structure, which is 7. That means 7 there are translations or rotations, that is degree of freedoms in the structure that is not solvable easily. So we have to go for higher analytical methods to solve this type of problems. Okay. Now for the 2D truss, this is the 2D beam. The 2D truss, similarly the equation becomes 2j minus RE. Now RE is 3 because here it is roller 1 and here it is pin 1 as 2. 1, 2 and 3. RE is 3. Joint is 6. 1, 2, 3, 4, 5 and 6. 6 joints. So here the equation becomes gives 9. Therefore the kinematic indeterminacy of this truss is 9. Therefore 9 there are degrees of freedom, that is we need to solve using complex method. Now what is the comparison of static versus kinematic indeterminacy? Static indeterminacy mainly is based on forces and reactions, and it is very important part in classical analysis. Whereas kinematic indeterminacy is focused on the unknown displacements, and it is very useful for matrix method, that is strictness method. Okay. Now the main part is why do we study this? What is the need of this study and what is the applications? What are the applications? That is, the indeterminacy mainly defines the structural analysis complexity. How complex is the structure, or how easily it can be solved, or how complex process we need to use to solve the structural component, their reactions and their degrees of freedom. Okay. So for static indeterminacy, it is based on unknown over equation, that is unknown forces over the equilibrium equation available, and how much extra unknown we are need to solve. Whereas kinematic indeterminacy is dependent on the degree of freedom in the structures. Okay. Next, static indeterminacy helps using is solvability using equilibrium equation only. That is, equilibrium equation is enough to solve it or not. And whereas kinematic indeterminacy is guided through the numerical and computational analysis like strictness method, matrix method for solving a complex structure. Both are vital in model engineering analysis. Both are always equally important, but more complex is kinematic indeterminacy solutions, and easier the part is for static indeterminacy structure. Now, for structural design analysis of modern structures, both are important. Therefore, this topic should be rigorously practiced, and problems should be solved more and more to get fluency in solving these type of problems, as well as to memorize the equations with understanding and application uh, towards the future is very much important for this topic to study. Okay, thank you. Let us go for another topic some another day. Thank you very much. Thank you.